Hello, and welcome to Lecture 5 of Electric Charges and Forces in Phys 1201. And in this lecture, we're continuing to look at electric fields, and in particular, look at how our knowledge of electric fields can help us to figure out some other things. At the end of the last lecture, I looked at a situation like this with two equal magnitude charges of opposite sign, and a point out here opposite the center point between them, and drew the E field there. And this time let's calculate it. But first, let me just explain something that I just went ahead and blithely did there. I did a vector addition of the two E fields due to the two charges to get the total E field there. And you can see why that is if you just think back to what the E field means. So the E field here at P we could get by putting a probe charge there. Remember, there's no charge at P, but if we put one there, there would be an electrical force on it. And if we divide that by the charge on the probe charge, that gives us the E field. But think about how that force is put together. It's a sum. It's a vector sum of two forces, one due to this charge and one due to that charge. And each of those forces is proportional to Q probe. And so when you then divide out Q probe, all you're left with is the individual E fields due to these charges added together vectorially. And so that's all you have to do. When you have multiple charges and you want the E field at a point, you just add up the E fields at that point due to all of your charges. So let's go ahead and do that. We already saw that we're the same distance from these two charges, and they are the same size. And so these two fields, E1 and E2, are the same magnitude, and they're at the same angle except flipped side to side this way. And so the x components of these two will cancel out, and we're going to be left with just the y components adding together. So in the end, our E total is going to be nothing more than E1y times 2, because E2y is the same. That's it. So there it is. And I'll note that E1y is negative. So that should be it. Really, all we need is E1y. And if you look at the trig that I've already set up here, E1y is going to be E1 sine theta, where this angle theta here is the same as this angle theta here. So let's go ahead. We're going to need the magnitude E1. So let's get the magnitude E1. So no vector symbol, I'm getting a magnitude. And we know how to do this. It's K magnitude of Q1, well, the magnitude part doesn't really matter, it's positive anyway, over, and I've called this distance here R1, so we need R1 squared. And you can see, if we just pull this R1 out here, where once again, this is theta, this is R1, this is 3 centimeters, and this is 1 centimeter. Right? This is 2 centimeters between the charges, and so down to here is 1 centimeter. And so we know that's a right angle, so R1 squared is just 3 centimeters squared plus 1 centimeter squared. And at that point, we know everything we need to know to get E1. I'll just write it all out here. And if you plug that into a calculator, you're going to find that that is 4.5 times 10 to the 4, and let's just look at the units. Meters squared in the denominator are going to take out those meters. This coulomb takes out one of those coulombs, and so we get newtons per coulomb, as we should for an E field. Now, E1y. So E1y is just E1 sine theta. Now it's tempting, we could come up here and use this triangle to get theta by doing inverse trig and then plug that theta into the sine theta. But that's too much work. Look, sine theta is just opposite over hypotenuse. We know the opposite and we know the hypotenuse. So we can just use that. So I'm just going to go ahead and say, careful, E1y is negative E1 sine theta, right? Look, it's pointing down. So negative E1, and then this is just going to be the 1 centimeter. And I don't even really need to worry about the units because I know it's going to be meters top and bottom, and they're just all going to cancel. And so finally, our E total, we already know, is just going to be 2 E1y j. So negative 2 E1, all of this stuff, which I'm not going to write out again, j hat. That's it. So now we're basically done. So you can plug in that 4.5 times 10 to the 4 newtons per coulomb and so on, and you're going to get negative 2.8 times 10 to the 4 newtons per coulomb j hat.
At one point in calculating that electrical field, I used a slightly subtle argument. And it's an important argument, so I want you to see whether you can use the same sort of argument in a similar situation. So here we have two identical positive charges, and I want to know which way the E field points at the place that I've labeled P.